choose one of you. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for this opportunity we have just to study your creation. Just give us insight into this subject of topology, Lord. In your name I pray. Amen. So, yeah, guys, I've told you already before, but we're planning to use Introduction to Topology by Theodore Gamelin and Robert Greene. And, it's available in Dover. And so this is more or less what I'm covering. Trying to stick to the book, more or less. But then I'm also interjecting, because I think the discussion in, oh goodness, I forget the name of the author all of a sudden. You guys tell me how to spell it? What is it again? J? A-N-I-C-H. So this, and it's also, is it Introduction to Topology, or is it just Topology? I forget. Just Topology. And so we have Gamelin and Greene. The book I'm holding, Intro to Topology. So I like the Gamelin book because it has a really healthy mix of analysis and also topology in a slightly unusual way. I mean, a lot of topology books you look at, they're more of kind of abstract set theory. They're more decidedly pure and more detached from, say, applied mathematicians who study, say, differential equations or something. There's inroads to the other parts of math in this book, and I think it's healthy. Now, Yannick, or however you say that, that book is beautiful and perhaps less applied, but it lacks an important feature, which is homework. So I couldn't really use that as the book since I don't have time to write up topology homeworks, But at the same time, I was just so enthused by the discussions and the pictures and how fast he gets to important ideas with an economy of words. I think it's a good book to read alongside Gamelin. I think you read both of those together and we have discussions, you're going to get a pretty good understanding of topology, especially after you do the problems that I assigned you. I don't have any fixed due date in mind, but you should start working on them, all right? And I'll try to post things, course content. But I sent you emails too, right?
About the class syllabus?
Yeah.
I didn't guess this all.
Yeah, I've sent 2 or 3 emails. I think I always included you on the list since you expressed your interest last semester. But I will refer to you as Dr. No. Let's see here.
I don't know anything.
You don't know anything, but surely you know yourself.
I don't know myself either.
But that seems impossible. Let's see here. Okay. So I'm going to try to take a big old bite out of the first chapter of Gamelin. The title of the chapter is Metric Spaces. Now let me just take a step back and tell you the bigger picture of what we're doing. The idea of this discussion is to look at metric spaces because they're the sort of first abstraction from just plain real analysis. So I think 3 of you have had real analysis. 2 of you have had real analysis. Are you 2 taking real analysis right now? Yes. Okay. It's not actually going to be a deal breaker because real analysis is so far down in the weeds that we're kind of up in the clouds a little bit. It won't really matter too much. I don't think I'm going to confuse that course at all right? On the other hand, you'll appreciate some things you're doing in real analysis later on because of what we're doing. I think it's going to be a healthy interaction, these 2 courses for you guys. But metric spaces is sort of the next thing you might do past real analysis. A lot of times real analysis these days, it's studying the topology of the real line, the construction of the real numbers, continuity for functions from the reals to the reals. All right, so the next step past that is to talk about those ideas, but for what's called a metric space. A metric space, I'll soon define, is just the next level of abstraction. But past metric space, there's the concept of a topology. Every metric space can be viewed as a topological space, it turns out. But not all topological spaces can be viewed as metric spaces. right? The set of topological spaces which can be viewed as metric spaces are said to be metrizable. Actually quantifying when that happens, I don't remember how, but it's complicated. Okay, so anyway, let me not try to lead with what's complicated. Let's just talk about what's a metric space. This will hopefully build up some intuition for the definition of topology in future lectures, all right? So almost every result that I'll show you today foreshadows a topological definition, all right? So theorems in metric spaces end up becoming definitions for topology, is one kind of theme of this book, which is a healthy and fruitful theme. Now, so first of all, we need to define a metric. So here it is, definition. A metric on a set X, all right, is a function, real valued function, on the Cartesian product of X and itself, all right? And typical notation would be something like D maps from X cross X to the reals, all right? And I don't have to put the reals there. In fact, without loss of generality, I could replace the reals with 0 to infinity, all right? Because here are the axioms for a metric. Axiom 1, the distance from X to Y is greater than or equal to 0 for all X, Y, and X, right? Axiom 2, the distance from X, Y to X to Y is equal to 0 if and only if what? X is equal to Y, very good. The distance from X to Y is equal to the distance from Y to Z. No, X. Okay, for all X and Y. So, you know, I would say it's like going to and from work, but too many of us live in stupid locales where you can't have one-way roads and then everything gets messed up, you know? Even here, like changing lanes, coming and going, I don't know, it could be all kinds of things. But yeah, the distance between 2 points should be symmetric. And by the way, I'm calling D distance, so it's also known as the distance function. The distance from X to Z is less than or equal to the distance from X to Y plus the distance from Y to Z. All right. And again, that's for all X, Y, and Z in X. This is a metric. Well, a metric space is what? Is the pair X and D. This is a metric space. It's a set together with a distance function. Let's see here. The label, so number 1 is that the metric is non-negative, right? Number 2 is that, what's that called? What's that again? Indiscernibility? Huh. That seems like, yeah, you can discern if X. Well, indiscernibility. Interesting. I know that 3 is definitely symmetry, and 4 is, by universal agreement, the triangle inequality, right? You can kind of picture that. But actually, so something to notice here, I mean, I've taught a lot of you linear algebra, right? And there we talk about norms, right? And a norm has what? It has to do with, there's some properties about the addition of vectors. If you look at this, is there anything about addition here at all for the points in X? You notice there's not, right? The addition here is taking place for the distance function, not at the level of points. So there actually is no assumption here that X has even some kind of like operation of addition or anything. It's just an abstract set. It could be a disk, it could be a triangle, it could be a grid of points. It could be a lot of things. All right, there's no vector space structure here at all. Okay? I mean, we could take a vector space and put a metric on it, that's true, but the concept of metric space is much more open. Okay? So on the reals, what's our typical metric? What's the distance from A to B? B minus A, all right. And I'll also take the absolute value. There we go. See, that's classroom, that's participation and interaction. When two people answer a question in stages, it's like the ultimate form of, what's that? 50%. Give 50% each, okay. R2, the distance between, distance between 2 points in the plane, what's our usual song and dance? Distance from A to B, we do what? Sum I equals 1 to 2, B sub I minus A sub I squared, right? And the square root of that. So this is the usual Euclidean distance function. I mean, some of you learned this in middle school, right? The distance between 2 points. This is the 2-point formula for the distance between 2 points. And of course, we can also talk about the Euclidean distance in Rn. How do I do it? Just erase my 2, put an n, erase my 2, put an n, there you go. This is the Euclidean distance in Rn. Right? So Rn, some people would say that Rn paired with this distance function is Euclidean space. Right? Because it's Rn with the Euclidean metric. Now, there are other kinds of metrics that we could put on Rn. Right? So my third example would be, how about if we write the distance between A and B is the sum I equals 1 to n of the absolute value of B sub I minus A sub I. You can actually prove that this is a distance function. So just the sum of the absolute value of the differences in the coordinates. There's also another example. You can let the distance from A to B to be I think the max of the absolute value of B sub I minus A sub I such that I equals 1 to n. This will define a norm on Rn as well. These are different concepts of distance, but these all provide metrics on Rn. Now, so let's see here. He has another example, a couple of examples which are kind of a little bit more exotic, and I think I'll include them because they help the discussion here. And so another example is on page 3. He's like, let S be a set and let B be S, Barbra Streisand, right? It's actually a set of bounded functions. From S to R, I suppose. All right? And he says that you can define a metric on this, all right? The distance between F and G, it could be equal to the supremum of the absolute value of F of S minus G of S, such that S is an S. He said this makes the set of bounded functions on S into a metric space. Well, that's a little bit weirder, isn't it? Yeah. I could draw a graph, for example. Here, S could be, say, I don't know, the interval from 0 to 1, right? So I could actually think of this directly. You know, I've got one function f, and I've got another function g, like that, right? So here's my g, here's my f. And so what is this metric? How is this metric measuring the distance between these two functions? Yeah, right. So this, so here's like a typical S in S, right? And so the value of f of s minus g of s is just the distance between the graphs. So the smallest it is 0, right? But the supremum is what? It's the...
I don't know what it
Fair enough, but you'll learn that in a lot of detail. The supremum is... In fact, I'm even... Well, I say I'm about to promise teaching that to my Calculus 2 students, but they may beat me down before I actually do that. Don't worry, we'll see. But supremum is the so-called least upper bound. So if you have a set of real numbers, all right, and if it's bounded above, all right, and if that set is non-empty, then the least upper bound property for real numbers says that there exists a smallest upper bound for that set. And that smallest upper bound is what we call the supremum. Now, if it's actually attained, if it's actually in the set itself, then it's also called the maximum. Right? So supremums can be maximums, but not always. Supremums can be like limit points, so to speak. Like it can be just outside the where you want to get to. We'll talk more about that. But here, like the supremum, I think, is at 0, isn't it? It's like this looks to me that that's actually the distance from f to g. It's pretty easy to see that we have the indiscernibility axiom, we have the non-negative axiom, we have the symmetric axiom. To me, the only thing that's not immediately obvious for his example is the triangle inequality. So, I'm going to go on, though. I'll let you guys look at that if you want. Another example he gives, and this one, you know, this example is kind of like, I wouldn't have known right off the top of my head that you could define a notion of distance between functions. That's a little bit surprising. Yeah. Oh. I do think we'll come back to that. Let's see here, another example, and this is a very greedy sort of meta example. Any set, any x, whoa, any set x. Any set x can be made, is a metric space with respect to the discrete metric. And what's the discrete metric? Distance from x to y is equal to? Zero if, yeah, that seems like it's not up for grabs, right? 0 if x is equal to y, it better be that. Because if we don't, I mean, that has to be, that's an axiom, we're stuck with that. And what else? I guess you could put anything here, but, I mean, any positive number, but 1 is what he does. This defines the axioms for a metric. I mean, it satisfies the axioms for a metric. It's certainly non-negative. It's symmetric, right? If x is not equal to y is not equal to x. And does it satisfy the triangle inequality? You can check the cases. It does. So what I said earlier about some topological spaces not being metrizable, I must be forgetting some fine print there, right? Because this would seem to metrize any topological space, because a topological space is first a set. All right, it's going to be a set that satisfies a couple of axioms. We'll see. So I must be forgetting something about metrizable when I said that earlier. I can see that from this example. This would be a fun one to use on your children when you have them, if you don't already. None of you have children. I think that's safe to say. They ask you, how far is it to where we're going? And you say, are we there yet? They say, well, no. The distance is 1. 3 hours later, how far is it to where we're going? Are we there yet? No. The distance is 1. Right? It could be fun. I use the discrete metric with respect to how long it takes. They ask me how long it's going to be till we're there. I always tell them 2 minutes. Doesn't matter if it's a day trip or 2 hours or 20 minutes, I will say 2 minutes. I have taught the children not to ask me how far it is to where we're going. So they just immediately route the question to Ginny now. So, yeah, poor Ginny. Okay, now, next concept, open ball. What's an open ball? So here, B, his notation, Bx semicolon r, it's equal to y and x, such that the distance from x to y is less than r. Right? This is a open ball. What's the center of the ball?
Is it R?
Nope, that's the radius of the ball. This is the radius, yeah. No, the center's x, yeah. Looking at the book, that's cheating, but it's okay. Ah. Well, yeah, I appreciate that. I'm not very good with countability, so it's an issue for me. Dr. Sprano's much better at counting, especially infinite things. Anyway, what he says here, he says the balls centered at x form a nested family of subsets of x that increase with r. All right, so in other words, comment, by the way, if r1 is less than or equal to r2, then the ball centered at x, radius r1, is a subset of the ball centered at x with radius r2. Of course, this is familiar to us from our experience with, geometric balls in the Euclidean plane, right? But this is actually, we could prove this directly from the definition of a metric for an arbitrary space. What's that? In the plane? Oh yeah, a disk in the plane. Right? Yeah, I just always think you're right. It's like calling disks, like talking about calculating the volume with a double integral, Or, well, I mean, you could, but I shut up. So how would I prove this is a subset of this? If we let z be an element of the ball of radius r1 centered at x, suppose that r1 is less than or equal to r2, what's that say? The distance from x to z is what? It's less than r1, right? Which is less than or equal to r2. Voila. Z is an element of the ball centered at x with radius r2. It is that simple. All right. But there's more. Moreover, the union over r greater than 0 of the ball centered at x with radius r is equal to x. Is that obvious? Why is the union of all balls, why does that hit everything? I mean, if we pick x, right? First of all, we're assuming we can pick an x. So suppose the set is non-empty, right? We pick an element x, right? Then what? Ah, okay. What would the, what if it's a single point set? I think there's something missing here. Because an open ball doesn't contain its, I mean, you can't have an open ball containing just one point, can you? Oh, with the discrete metric, yeah. Ah. I guess the thing I'm struggling with is x in a ball? I mean, can you guys tell me why? And this is probably something stupid, but is x an element of a ball of radius x comma r?
Yeah. Yeah, because
Or let's be more specific. So, I mean, I'll be specific. Let's say radius 1 for the sake of specificity. I'm dealing with existence here. I don't want to beg the question, is there an r?
Right.
So what was the argument?
Well, I think the distance from x to x is just going to be 0, right?
Okay, very good.
So it's going to be less than 1.
Okay, great. My concern is unjustified. So x is always in a ball of any positive radius centered around x. So that gives us that x is contained in this union. What about any other point? So I let y be an element of x, y be an element of big X, and I let the distance from x to y be equal to what? Oh, maybe you let this plus 1 be equal to the radius. Is that what you guys are going with? Something like that? Then y is an element of the ball of centered at x with radius r. But y is arbitrary, so we've shown that every point in the metric space is contained in an open ball. Oh, okay. I mean, this makes sense if we think about our intuitive pictures in the plane, open balls, right? But, so I'm just taking a second to prove some things, okay? I'll try not to do that for everything, otherwise we won't get anywhere. But the other thing we could prove, also, the intersection over all positive radius balls centered at x is equal to just the set containing x, the singleton. All right. Now, furthermore, a few more definitions. If y is a subset of x, then x in x is an interior point of y if what? It's an interior point of y if what? Right, if there exists an r greater than 0 such that the ball centered at x of radius r is a subset of y. That's an interior point. So you can find an open ball around the point which is inside the subset. And the set of all interior points of y is called int y. All right? So set of all interior points of y is denoted int y. And that, of course, is going to be a subset of y. All right. All right. And furthermore, a definition, y is open if and only if the interior of y is equal to y. All right. And since it's immediate that, why do we know that the interiors are a subset of y? I think that goes back to what we already proved. If y is an interior point, there exists a ball of radius r around it, which means that the center is also in that ball, which means that the center is inside the set y, which is to say that the interior point is inside y, which is to say that y is containing the interior of y. That's true generally. The interior is always a subset of a given set. All right? But the converse, right? This means also that y is what? A subset of the interior. This is a special property that's only true for open sets. Okay? Now, theorem 1.1 is an open ball in a metric space is an open subset. And if you look at the proof of theorem 1.1 in the book, it's very simple. What he does is he takes an arbitrary point in the open ball, and he shows that there's a little open ball around that point, which shows that an arbitrary point's interior, which shows that it's open. Let's see here. Well, I'm going to move along here. Theorem 1.2 is that the interior is an open set. So if you take any set and look at its set of interior points, that is an open set, which you can write as int of y is equal to int of y. In other words, the interior of a set is the interior of a set. So there's just the inside. There's like no holy of holies, right? It's like just, sorry, I'll try to resist any temple humor going forward. What else do we have here? The union of a family of open sets, the union of a family of open sets of a metric space is an open subset. See here. Something I was going to mention before I got too far away from this was what do the open balls look like for the plane? Right? So if you asked me to visualize the open ball in this space, I couldn't do it. Can you visualize infinitely many functions that are bounded? I mean, the best I could do for that would be something like that. But, you know, that wouldn't even do it because it's just bounded, right? So 100's bounded, a million's bounded. We don't have enough board space for that one. At a minimum, we'd have to use a logarithmic plot or something. Anyway, but in the plane, in R2, I can actually show you a picture. Oh, phooey. Probably shouldn't have done that. So let's see here, R2. Of course, you know that, you know, this is the ball centered at 0, radius, let's say radius 1, with usual, you know, Euclidean metric, right? So the distance, you know, in other words, we're looking at distance from 0 to, say, x comma y being less than 1. Short first class? Short first class? Ah, cool. I don't think I've hardly said anything yet. So this would be the open ball with the Euclidean metric, right? Radius 1, because it's the set of points that have distance 1, you know. If we look at the open ball, if we look at the distance, you know, distance from 0 to xy being defined by the sum of the absolute value of x plus the absolute value of y, if that's less than 1, what does that set of points look like? Of course, I mean, you know, I usually fuss and go, it's like this, right? Those points aren't included. It's inside those. That's the open ball, right? What's that, this one? Zero. These points are not included, but almost included. Sort of, yeah. Those are the, so yeah, it's something like this. If I did it right, it'd be a diamond. If you look at the absolute value of x plus the absolute value of y equal to 1, that gives you like y is equal to 1 minus x for the upper leg, and y equals to 1 plus x for the other leg. And then down here, you've got like y equals to x minus 1 and y equals to minus x minus 1. Bits of those lines satisfy this inequality. Well, those satisfy the equality there. Being less than that makes you inside the, I would say unit diamond, but actually this is the unit ball in the, you know, above the distance function metric. What was your question, Sam? Metric what? It's 3. Very good. Yeah, that was the 3. So this is case, this was, you know, this is 2 for R2, this was 3 for R2, and finally 4 for R2. The distance from 0 to, say, the point xy being equal to the max of x and y. Well, that, you know, if you look at the collection, the so again, this was B 0, comma 1. You know, guys, he puts a semicolon in the book, and I'm just forgetting it sometimes. I'm sorry, it's just going to happen. But here, the ball with respect to the case 4 here, sometimes called the max norm, the unit ball centered at the origin, radius 1, just looks like just the unit, you know, unit square. So these are all disks, but these are disks with respect to different notions of distance in the plane. And if you think about it, what would it take for a set in the plane to be an open set? It what? It contains, open set in R2, right? If you think about it being, I don't know, could be something like this, right? The point is, if I pick, these are supposed to be holes. If I pick any point in this set, right, like this one, then you can see that it's open, that point's an interior point with respect to the Euclidean metric, right? Because I can put a little circle like this, and that ball of radius, whatever it is, say epsilon, is inside the given set. Let me give it a name, S. Right? But by the same token, you could draw a little diamond, right? You could draw a little diamond. So that would show that it's an interior point with respect to the, case 3 metric in the plane. And of course, you know where I'm going with this, you could just as well draw a little open square around it, right? So it's not hard to convince yourself that if a set is open with respect to one of these notions of distance in the plane, it's going to be open with respect to any other one. Yeah.
Is that true for all cases, that it's open with respect to one metric and with respect to all metrics?
I don't think that would generally be true. I think that there would exist choices of metric on an arbitrary space which would give you different notions of open set. Yeah. I think that the discrete metric would give a different notion of open than the Euclidean metric. I'm going to move along. Right. So theorem, I'm going to read some theorems in here, all right? The union of a family of open subsets of a metric space is an open subset of X. How would you prove that? If you have a union of sets, if you pick a point in the union, it's in one of the sets, right? But if the sets are all open, that means that the point that you picked is inside a set for which there exists an open ball around the point. And that open ball is contained in one of the sets. But if it's contained in one of the sets, it's contained in the union. Therefore, an arbitrary point in the union of sets is again an interior point. Theorem 1.4 says a subset of a metric space X is open if and only if U is a union of open balls in X. Now that's a little bit less obvious to me. So he's saying that open set that I just drew right there is a union of open balls. What's the catch? You need what? Well, let's just focus on the Euclidean metric. Just say Euclidean. So actual honest-to-goodness open disks. The catch is that you have to use infinitely many of them, right? So it's kind of like bubbles of, it's like bubble, bubble. Here's the proof. If I could be so foolish as to do that one. Where was I? Come on. So he says by theorems 1.1 and 1.3, the union of open balls is open. So anyway, here's subset U, subset of X is open if and only if U is union of open balls. So the proof begins with this direction basically saying done already. In fact, I described part of that to you. The thing I didn't prove in class today was that an open ball is actually open. That's in the book. So you prove an open ball is open. Take a union of open sets. I just explained to you without writing on the board why that was open. So a union of open balls is open. That's one direction. I'm sorry. Sometimes one direction comes into things. I try to avoid it, but the other direction, on the other hand, why is it that if U is an open subset of X, it's a union of balls? All right, so suppose that. And what he does, he says for each X in U, there exists an R of X, right? It says for each X in U, there exists R of X positive, right? Such that what? The ball centered at X of radius R of X is what? X, right? It's an interior point, so that means that that ball has to be, by definition, contained, like you said, contained in U. All right. So then, okay, so that's great. He says, utilizing U as an index set for a union, we obtain an expression. U is the union over X in U of the ball of radius X comma R of X I wonder if you've seen a union like that before. Right? We usually talk about countable unions, like union I equals 1 to infinity or something. But the concept of union makes sense for arbitrary index sets. The definition is still what you've been taught. A point is in the union if the point is in at least one of the sets, which are being unioned. Right? So why is X, if X is a point in U, why is, let me not use X. Let's say X naught is a point in U. Why is X naught in this union? Because X naught is in the ball of X naught semicolon R of X naught, right? It's the center of that ball. It's inside the ball. We proved that already. So it's in there. But X naught's an arbitrary point in U, so that's every point in U. So it stands to reason, well, there you go. We just wrote U as a union of open balls. Yeah. Do there exist examples where it has to be an uncountable union? I don't know. I don't know. I would assume so, but I don't know right offhand. A nice example he gives in the book is just the unit square in the plane, you know. This is a finite, I mean, it's a bounded subset of the plane. It's pretty simple, but you cannot write that as a finite union of open disks. But I bet you could write it as a countable. It seems like countable is possible.
Well, Kane was saying that since all the rational numbers are
Mm-hmm.
At least for Euclidean, you should always be able to do it as.
I do think that the itch you guys are trying to scratch gets a definition and a discussion in later sections, so keep it in mind. Next theorem up here is that the intersection of any finite number of open subsets of a metric space is open. Finite intersection of open sets in metric space is open. Mm-hmm. So I'll look at the proof of this one with you. So let U1, U2, UN be open. Pick Z in the intersection. Right? By the way, if the intersection of them is the empty set, is the empty set an open set? Does it? Is the interior of the empty set equal to the empty set? Yeah, this is vacuously true. So yes, empty set is open. Yeah. So okay, well that's settled. So if we're not interested in that, there must be a point in the intersection, right? What does it mean to be in the intersection? Ui for all I, right? Thus, there exists what? Let's say delta I greater than 0, such that what? Such that the ball centered at Z with radius delta I is a subset of Ui. Why can we do that? I mean, these are all open sets. Z is a point that is in each one of these open sets. So for each open set, there exists an open ball contained in that set, right? There exists a radius that makes the ball. Okay. And then so what we do is just let delta equal to the minimum. This is a finite set, so we can do that. Let delta be the minimum of all these deltas, right? And then if you look at it, we'll have that the ball centered at Z of radius delta is a subset of the ball centered at Z of radius delta I for all I. I know that because of the thing we argued earlier, the nested ball property. Certainly delta is smaller than delta 1, delta 2, delta 3, delta n. So it stands to reason that the ball of minimal radius is contained in all the other balls centered at Z, and so forth. So then what this condition says is what? It says that B of Z comma delta is a subset of the intersection I equals 1 to n of Ui. In other words, we've just proved that Z is an interior point of this finite intersection, which then proves, of course, that an arbitrary point in the intersection is interior. Consequently, the intersection of open sets is open. I missed an important word in my last statement. Finite intersection of open sets is open. You notice there was no finiteness in the previous discussion, right? The arbitrary union of open sets is open, but the finite union of open sets is finite intersection of open sets is open. What about the infinite intersection of open sets? Yeah.
Is it because you would need delta to be the minimum of
That's probably one way of looking at it. Let me just give you an explicit example. How about this? What if we let, say, un equal to, say, 0, 1 over n, for n equals 1, 2, 3, da, da, da. Look at the intersection of un, or n 1 to infinity. What's that?
That is open.
Oh, that is open? Dang it. Son of a gun. There you go. So this would be 0, right? I haven't proved that, but you could. Welcome to your real analysis homework. Proving that is what you shall do.
My real analysis homework for this week is drawing Venn diagrams.
I'm going to have to talk to Dr. Joseph. Anyway, well, Venn diagrams are important. You'd rather grade those? Yeah.
So is what we're doing is taking the axioms of the metric and showing that they induce the axioms of the topology for topological space.
You've seen through my ruse. Yes, this is the point. Is the chapter that we're going through this chapter on metric space. So Gamelin starts with a chapter on metric spaces. We're going to try to see all of the major features of metric spaces, and those will hopefully motivate why we define topologies as we do. But yeah. Now, we haven't proved that, I mean, this is an example on the real line. So why is a set containing just a point not an open set with respect to the usual distance function on the reals? So why not open? What'd you say? Uh-huh. So you're like, suppose there exists an r greater than 0 such that the ball centered at 0 of radius r is a subset of the set containing 0. I think then if you look at r over 2 is an element of the reals, right? And and r over 2 is an element of the ball centered at 0, right? Of radius r. I mean, I can draw a picture of what's going on here. Here's 0. Here's the ball. Here's r over 2. You can go back to the axioms and prove it's there in the ball. It meets the condition. It has distance less than r from 0. It's in the ball. Is it 0? Well, we assume that r is a positive number, right? So r over 2 is also a positive number. This is absurd. We can't have r over 2 as an element of the set that which can just contain 0.
Or we found a zero device.
No. Therefore, there does not exist an open ball of any positive radius. We just did an arbitrary radius, right? It's important that you show that this doesn't work for arbitrary positive r. Otherwise, your real analysis instructor should rightly jake off points. If you're just like, well, if you look at a ball of radius 1, it doesn't work. Like, well, that's one of infinitely many cases that you need for the proof. I'll give you 1 over infinity partial credit for that, right? No. So anyway, the point is, no ball can possibly be an open ball around 0, which just contains 0. Every open ball around 0 with respect to the Euclidean metric, right? Now, the discrete metric, on the other hand,